An important question that we should now ask is, how do we convert from Cartesian coordinates to polar and vice versa? And this is where coordinate transformations really come in. Let's say that we have coordinates given in polar coordinates. This means that we have a point with coordinates r, theta. How do we go from polar to Cartesian? This is relatively simple. If you look at the axis and the comparison between Cartesian and polar, you'll see that converting is mostly just about, in this case, x will be r times cos theta and y will be r times sine theta. Therefore, to convert from polar to Cartesian, we use x equals r cos theta and y equals r sine theta. It's this simple. The other thing you can ask is, how do we do the reverse? How do we go from Cartesian to polar? Say we have a point x, y, and we want to calculate what r theta that corresponds. That's relatively straightforward as well. If we start with this, we could see that, for example, if we have a look at y over x, we would get r sine theta over r cos theta. We could cross out the r's as tangent theta, and therefore a way to get theta is essentially by getting the arctan of y over x. How do we get r? We could also start with these coordinate transformations, and for example, if we add x squared, y squared, we'll see that we'll be doing r squared cos square r plus r squared sine squared theta. We can also write this as r squared sine squared theta plus cos squared theta. The order doesn't matter. The thing that matters is that this is 1, and therefore we know, just from geometrical arguments as well, that r squared is equal to x squared plus y squared. And this obviously implies that the coordinate transformation that we need is r plus or minus square root of x squared plus y squared. If we want to go from Cartesian, where we have x, y, into polar, where we have r, theta, these are the coordinate transformations that we need. You can memorize them, or provided you understand these simple geometrical arguments, you can always manipulate them to get there. And it's theta equals the inverse of the tangent, that's arctan of y over x, and r can be plus or minus because we're dealing with a square root. And this is where it's crucial for you to think. When you convert between Cartesian to polar, there are multiple solutions, there are multiple angles that will be a solution to this, and also they will be linked with specific solutions. As we'll see in an example, the best way is to understand where your point is in Cartesian, and when you calculate it in polar coordinates, make sure that it ends up in the correct quadrant. If you get it in the correct quadrant, it means your answer is correct. If you end up somewhere 180 degrees from it, it's definitely wrong, and it probably means you need to flip the sign of r or pick another theta. Let's try to apply this, going from polar to Cartesian. And in your lecture notes, you have the example where you're given r theta equals minus 4 2 pi over 3, and you want to convert this into Cartesian, which means getting some x and y. How do we do this? We've seen we only have to apply this coordinate transformations. In this case, for x, we have minus 4 times cos of 2 pi over 3. This cosine is minus 1.5. Therefore, we end up with 2. This will be 2. And for y, we also have minus 4 times now sine 2 pi over 3. Sine 2 pi over 3, square root of 3 over 2. And we'll be dividing by 2, and we end up with minus 2 square root of 3. And we can then write this is minus 2 square root of 3. And the point in Cartesian coordinates is then given by x, y equals 2 minus 2 square root of 3. And this would be the final answer. If you want to convert from polar to Cartesian, it's as simple as this. And there is a single route to get there. You don't really need to check. If you wanted to, you could, but coordinates in Cartesian are unique. There is only a combination of x, y that will give you that coordinate, and therefore there's no major need to check what you got in the end. What about the reverse? What if we want to go from Cartesian to polar? Let's try that. Now we want to go from Cartesian to polar. In this case, and following the example, it's also in your lecture notes, we have a point that's x, y equals to minus 1, minus 1. We can even start by plotting it in Cartesian axis. This will be here. This is the point. This is very important because once you convert to polar, you want to make sure that you end up in the third quadrant. In order to do this, you need the coordinate transformations from Cartesian to polar, which we've seen. You can write them as r equals plus or minus square root of x squared plus y squared. And the other coordinate transformation is theta equals arctan of y over x. All you have to do then is process these. In this case, we'll have a look and we see that we'll have plus or minus 1 plus 1. That's plus or minus square root of 2. And for theta, we have arctan of 1 because it's minus 1 over minus 1. And there are multiple solutions for this, but one solution is pi over 4. If you're really sloppy, you could just say, oh, I'm going to take the positive solution because I'm a physicist. And the answer would just be, in this case, r theta would be plus square root of 2 pi over 4. And you'd be very happy. The problem is, if you don't check it in the Cartesian axis, you're very likely going to make a mistake. There's almost a 50-50 chance that is going to happen. In this case, let's say that this was the correct answer. If it is, you need to end up here. Let's process these coordinates then. Pi over 4, you would move here. That's pi over 4. And then you move this way because r is positive. You actually end up in the wrong point. You would end up in 1, 1. This is incorrect. If you get to this stage, you just need to make a choice. You go back after checking that one of the solutions really doesn't work, and you can realize that one of the ways to do this is you can pick an angle. In this case, if it's pi over 4, you end up here. In order to get there, you need to have negative r. This implies that one potential solution to this problem, or a set of polar coordinates that describe point minus 1, minus 1 in Cartesian, is to use minus square root of 2 pi over 4. Or if you're really keen for another solution where r is positive, if you already decided that you really want r to be positive, you need to find out which theta goes along with it, because you want to end up here. And if you also want to have a positive theta, what you need to do for a positive r is to add pi. And in this case, you would end up with 5 pi over 4. It is still important to understand that you can have many other solutions. You could keep adding or subtracting to pi, that would work. Or if you flip a sign in R, you can be essentially adding pi and vice versa. And this reinforces the aspect of there's only one way to write a point in Cartesian coordinates, but there's many ways to write them in polar coordinates. And therefore I would always encourage you to, whenever you're converting from Cartesian to polar, plot it. Check where the point is, so that when you get your solutions, which are multiple, you can make sure that you get the correct combination. And there's more than one correct solution, which is great, provided you've checked that it is correct. These coordinate systems, and specifically polar coordinates, will be used a lot, not only throughout physics 110s and integration and then in vector calculus, but also in physics modules like electromagnetism and in many other modules. And it's crucial that you know how to convert from polar to Cartesian and vice versa, because some problems are better defined, presented and studied in Cartesian, while others, especially those that have some circular symmetry, much better in polar coordinates. If you know these coordinate systems very well and how to transform them, we should definitely be moving on to something even cooler, which are coordinate systems that describe things in 3D. We'll see that we can have a very natural expansion of the Cartesian coordinate system, but also that there's two major extensions to the polar coordinate systems in 3D. One that relies on just adding a distance, like another r, and another which allows you to add another angle, which are spherical coordinates. And I'm still looking for my ukulele. I don't know if you've seen it, because I haven't seen it in a while, but maybe you have. See you in the next video.